It is with great joy that I introduce our keynote speaker for our fourth day of the DDON AI Symposium. Dr. Dimitar Filev is a Henry Ford Technical Fellow at the Ford Research and Innovation Center located here in Dearborn. He's conducting research in computational intelligence, AI and control, and their applications to vehicle systems, autonomous driving, and automotive engineering. Dr. Filev has published 4 books, over 200 journal articles and conference papers. He holds over 100 US and foreign patents. He is the recipient of the 2008 Nobel Winner Award of the IEEE SMC Society and the 2015 Pioneers Award of the IEEE CS Society. Dr. Filev is the fellow of IEEE and a member of the NAE. He is the past president of the IEEE Systems, Man, and Cybernetics Society in 2016 and 2017. Please join me in welcoming our keynote speaker. Thanks a lot, Dimitar, for being with us in our Dearborn Artificial Intelligence Research Symposium. We are glad to have you as our keynote for the fourth and the last day of our symposium. So today we'll be giving really an exciting talk about AI and autonomous vehicle. So please go ahead and start your keynote. Thank you.
Thank you, Marwan. I really appreciate the opportunity to talk about this topic with this audience. My talk will be about artificial intelligence and how it impacts the design of autonomous vehicles. I'm more used to the term autonomous vehicles rather than the more accepted term self-driving vehicles, but I will be using them interchangeably. We're all aware of about the unprecedented explosion of AI algorithms, software, and applications. According to one study that was done by Stanford University, the speed of AI algorithms doubles every 3 months. In other words, the rate of growth of artificial intelligence exceeds Moore's law for computing hardware. We can hardly think of any area of business that is not impacted by artificial intelligence. Not only that, there are technology areas that did not and could not exist without artificial intelligence, and autonomous driving is one of them. I would say AI drives autonomous vehicle development, and I'll be talking about this later. Design of autonomous vehicle is also one of those that is also stimulate the development and the progress of AI as a collection of multiple methods that are focused on one objective, and this objective is creating systems with human-like intelligence that can perceive, learn, make decisions, and act similarly as humans do. The early AI, the one that we know from the 70s and 80s, the one that is before the explosion of machine learning methods, was dominated by the idea of knowledge modeling. Knowledge models of the type if-then rules, expert systems, knowledge-based systems, etc., dominated the artificial intelligence in the previous years. The modern AI now includes, is essentially a technology stack that includes 4 main components. The first one, the foundational component, includes the computational platforms, sensors, vision and audio sources of data that is necessary for perception. Machine learning is one of the most critical components of artificial intelligence. It learns from data and summarizes the data into models and enable the predictive capability of AI systems. Conventional networks that now we call shallow networks and deep learning network models are the main components of machine learning. This branch of AI provides models for prediction and classification, and it is also known as predictive AI. The decision layer is a very important component of the AI. It transforms the models into action. Reinforcement learning, game theory, evolutionary computing, and other optimization methods are some of the key decision-making technologies. Well, the prediction methods have been rapidly developing since the introduction of deep learning. This second group of methods, known as decisioning AI, began to receive significant attention only in the last few years and is under very extensive development. The outcome of all that are the AI applications, which includes autonomous vehicles, robots, human-machine systems like chatbots, natural language understanding, and so on. So in summary, AI is a broad set of technology which includes machine learning, neural nets, deep learning, but it also includes decision-making methods. It includes also the conventional AI tools, etc. And all this is having big impact on the development of the autonomous vehicles. And speaking about the autonomous vehicles, I would like to outline three main architectures of autonomous vehicles. The first one is the so-called end-to-end learning or behavior reflex type of learning architecture. This is something that is, I would say, the grandfather of autonomous vehicles. Was introduced in 1988 by Dean Pomerleau at Carnegie Mellon, who demonstrated for the first time that if you train a network which maps the video input from a camera to the actions of the driver, then one can control an autonomous vehicle. And this type of approach, which is really neural net type of based approach, was further developed in the recent years by NVIDIA. And there is another small company, a startup from Cambridge University called Wave, which is promoting and further developing this interesting approach, end-to-end type of approach to autonomous development. The second major group of architectures for AV development is the so-called mediated perception group. And in the mediated perception approach, we see complete need for complete recognition of all relevant objects, such as lanes, traffic signs, traffic lights, cars, pedestrians, basically complete recognition of the scene on the road. The recognition results are then combined into a consistent world representation of the car's immediate surroundings. And to control the car, an AI-based engine is used to develop the decision policy. Almost all main players in autonomous development, including Waymo, Uber, Argo, follow this approach. I would say I would call this approach also DARPA Grand Challenge approach, because it was initiated during the early DARPA Grand Challenge competition, autonomous development. And the third group of methods for autonomous driving is the so-called direct perception method, which is a relatively new paradigm that was adopted, that adopts convolutional nets to learn a mapping from input image to the key perception indicators called affordance indicators, which essentially represents the state of the vehicle and the environment. AutoX spin-off from Princeton University introduced this approach about 5 years ago. And it is, this approach is promoted heavily by Tesla. Basically, this is the essence of the Tesla approach. One significant difference between the direct perception and the mediated perception is the use of the assumption of using maps. In the mediated perception, the scene that is identified through the perception is compared to a high-definition maps, while in the direct perception approach, there is no need for high-definition maps, and this is constitutes one of the main advantages, and of course one of the main challenges for this approach. Anyway, each of those three architectures are uses very heavily artificial intelligence. In the first approach, which is end-to-end learning, we see basically a predictive type of AI where the network is used simultaneously for perception and for decision-making. While in the second and the third approach, you can see that we have clear division, clear decoupling between the perception and control, which represents the driving policy. So these two tasks are decoupled, also in the direct perception approach. Now, speaking about driving policy, I want to talk more about driving policy because the perception is very well developed, and it's almost a commodity in autonomous driving. And what is challenging is how to make decisions in different situations, and this constitutes basically the challenge for the driving policy. The objective of the driving policy is to basically to develop a policy that is with minimal collision, where the number of collisions is zero for the vehicles that are driven by autonomous driving. Also, another objective is to optimize the vehicle performance and to achieve human-like type of driving performance, to optimize the speed to the extent to the speed that is allowed in the current road conditions and under current regulations, and of course to improve the overall efficiency, something that is possible when the vehicle is controlled without human in the loop. Some of the most common driving policy methods include rule-based and finite state machine methods. These are remnants from the old AI, which essentially introduce common sense knowledge and experience in the driving policy. They are reliable, they are very well defined, and I would say they are used by any of them, by all major players in autonomous development. Another important component is the reinforcement learning strategy for autonomous driving, in which we have a reward function that is continuously evaluated through interacting with the environment. I would say reward and policy are fancy names for something that we know as objective function and control algorithm. But in general, this policy, this reinforcement learning approach relies very heavily on use of simulation as a substitute for the environment, because we cannot do, of course, we cannot interact directly with the environment while developing the autonomous driving policy. Inverse reinforcement learning learns the reward function from the expert demonstrations, and in this sense, it is a very important addition to the reinforcement learning. And another approach is the imitation learning, which is end-to-end type learning of control strategy from the execution of an expert as a mapping from the state to the action space. Besides the first two approaches that are very well known, the reinforcement learning is the method that receives the most attention in the recent years, and that is the focal point of research on driving policy for all major developers of autonomous vehicles. Now let's talk briefly about reinforcement learning. Reinforcement learning essentially is a Markov decision process in which we learn a control algorithm through taking actions on the environment that maximize some notion of cumulative reward. The cumulative reward is encoded in the well-known Q function, is the cumulative reward. And the Q function is used to calculate the reinforcement action. It characterizes the quality of an action taken in given state and summarizes the successful actions for each state. The design objective in reinforcement learning is to find an optimal policy that maximizes the discounted return. Reinforcement learning has been known for over 20 years, but it did not make practical impact and practical progress for a long time. The situation changed about 5 years ago when DeepMind introduced the concept of deep Q network, the so-called DQN method, and other derivatives of it like double deep Q network, DDQN, deep policy gradient, DPG, etc. This is a convenient way to address the problem of stable learning, the Q functions as a set of two networks, target and current network. The temporal difference between the estimated predicted return and the current Q values is used to update the network weights by applying stochastic gradient, stochastic backpropagation. I see here a typo. Stochastic backpropagation to update the weights of the network. Needless to say, the simulator is a very critical component of the reinforcement learning approach. Here is an example on the next couple of slides, which I would like to share about our experience in applying reinforcement learning to the problem of designing driving policy. In this example, the reinforcement learning was used to develop level 3 driving policy for highway driving. The state vector is continuous, composed from continuous state variables, which includes the longitudinal and lateral velocity and the lateral position of the host vehicle, and the relative and the velocities and relative distances of the surrounding vehicle. So the dimension is at least 27, can be more than that, can be less than that, but it's high dimensional state vector. The output is interesting to note here. The output is discrete, and the output includes actions in longitudinal direction: maintain, accelerate, decelerate, and hard decelerate, and actions for in lateral direction, lane keeping left, the lane keep in the current lane, move to the left, move to the right. The reward function is composed by 3 components, which reflect the requirement for maintaining relative distance to the vehicle ahead, to maintain desired lateral position on in the current lane, and to maintain target velocity. During training, we utilized as a virtual environment various simulation tools, including Sumo and Unreal simulation engines, finite state machine, and data from manual driving vehicle simulator. The DDQN reinforcement learning algorithm was applied to high-level decision making. As I mentioned, the output of the reinforcement learning here is a set of discrete actions, and in order to implement those actions on the vehicle, we used a lower-level controller, which is a modified version of model predictive control, to do the trajectory planning and to follow the trajectory. The sequence of reinforcement learning decisioning and the path following is executed and updated every 200 milliseconds. Thanks to this combination of high-level DDQN and low-level trajectory following, the standard DQN framework can be applied to a variety of physical control systems. Now, our experience in this use case in applying directly the DDQN method was not overwhelming. I'd like to share this with you. It was in the beginning. It shows slow learning of the Q network and multiple crashes. I think I would explain this with the fact that conventional Q methods and DQN also does not have means for handling common sense knowledge, for introducing and for infusing information about the rules of the road, and they rely 100% on learning from data. And we believe that introducing this common sense knowledge is really very important in any type of AI method. So in order to address this issue, we introduced two major changes to the traditional DDQN approach. First, we augmented DDQN with as you can see here, with something that is like a filter of safety rules, which create a safety boundary around the actions that are recommended by the reinforcement learning algorithm. And second, the safe and unsafe state action combinations were stored in 2 different corresponding replay buffers versus the traditionally used in DDQN 1 replay buffer. And samples from those both buffers are mixed during training. This allows to mix the data and the knowledge during the learning of the Q function. And I believe that this is a very important and critical step in making reinforcement learning more realistic, because it allows basically to infuse subjective knowledge into the reinforcement learning algorithm. Here is how this modified reinforcement learning algorithm, which we call hybrid algorithm, looks like. The action that is obtained from the reinforcement learning controller is checked by the set of safety rules, and if it satisfies the rules, then it goes and it is placed in the replay buffer, and we apply the traditional DQN algorithm. If not, the safety rules provide a recommendation and a replacement for the action. So the action from the safety rule is taken, which is more conservative. And both the safe and unsafe actions are placed in the replay buffer. For that reason, I mentioned we have two buffers, actually, two replay buffers. And then we continue to update the network. So here is how this impacts this addition of the safety rules impacts the convergence of the reward function. You can see the reward function here with the safety rule filter versus the evolution of the reward function during training without that. So this safety boundary, we believe, is very critical, and there is a lot of opportunities here for adding more heuristic rules that come from different studies. In some sense, this is similar to the concept of the so-called RSS concept that was introduced by Mobileye, of using subjective safety rules to improve the safety of autonomous vehicles. We believe that there is broader opportunities here for improving the safety filters, and we are working on that not only by using safety rules, but by using other means. And I won't be talking about that now, but there is a very extensive work on that, how to make the reinforcement learning algorithms more effective and more safe and more realistic. Here is, let's see if this works, simulation. Here is a simulation of this hybrid approach that I mentioned, which was applied to highway policy for level 3 driving, and which is being now implemented and tested in level 3 autonomy vehicle in our group, by our group in Palo Alto. Some of the main, I would like to share some of the main open questions related to the application of reinforcement learning for driving policy. One of them is how can we explain the reinforcement learning policy in order to certify a controller that is not 100% predictable, especially in situations that are not covered during the training. The explainability, in general, explainability is a big problem, as you know, in artificial intelligence, and it is being now discussed very extensively by many researchers. The safety filters provides a very reasonable solution by creating a conservative safety boundary, but the general question about interpretability and explainability of the reinforcement learning solution remains open, and this is a subject of continuous research. I would say another major question in using reinforcement learning for designing driving policy is the question of the adaptation, how to adapt the reinforcement learning controller to a solution, to environment that changes, because we know very well that we cannot put in the simulator all possible situations that happen during driving. So these are open questions, and they are very challenging questions for research. Now let me move now to very briefly. I don't know, I have probably about a couple of minutes. I want to mention that we have been looking very extensively recently at the problem of explainability of the AI solutions. One idea of addressing the explainability is the idea of using alternative models that are more explainable to approximate the reinforcement learning solution. And here is the idea. we simulate the reinforcement learning agent as a black box after it is developed, after it is designed, and then use the generated combination of state and action to approximate it with an alternative interpretable model of the type of rule-based model or decision trees. Rule-based models, for instance, with rule-based models with fuzzy predicates are universal approximators. We know this very well. So there is theoretically there is no problem really to identify a rule-based model of this type that can approximate the Q network. So different types of rules can be used to approximate the reinforcement learning solution. For instance, here is a rule of this type. If the state is in this area or the state is in that area and so on, then we deal with action Y. And this can be done by essentially by clustering the state space into regions and then assigning to each of those regions a discrete output. So that way one can essentially approximate the DQN mapping with a set of rules, and I will give you on the next slide one example. Similarly, for the deep policy gradient DDPG methods, the approximation is of rules of similar type, but with a consequent which is functional, and because the output of the DDPG is a continuous function. So this is something that can be done to approximate also continuous reinforcement learning strategies. On the next page, you can see one example of a rule that is generated, that is automatically generated by approximating the reinforcement learning network with fuzzy rules. So although the rule is not completely clear, it still provides some way of interpreting and transforming into a linguistic setting the completely black box type of output that is generated by the reinforcement learning controller. Now, I want to make a few concluding comments about that, and that AI is really an essential part of the methods and tools for developing autonomous driving policies. Reinforcement learning is really the major workhorse in that direction, capable for generalization and summarization of a wide range of scenarios. It depends very much on the simulation tools and the simulation environment. Combining the rules with reinforcement learning provides opportunity for creating a safety boundary, which is including common sense knowledge. In other words, we don't have to learn from data something that is already very well known and can be that can be encoded in the form of rules. This allows to blend reinforcement learning with cognitive information and not only rules but also models, and to improve significantly the effectiveness and explainability of the reinforcement learning solution. And explainability and adaptation, and as I mentioned before, remain some of the main open problems in reinforcement learning. And to complete the presentation, in conclusion, I'll try to answer the question that probably I'll be asked immediately by almost everybody: when are we going to have a fully autonomous vehicle? And my answer will be trivial and casual, that it depends. It depends. I really think that it depends very much on the state of development of AI. We already talked about that a autonomous vehicle development is highly correlated with AI. So by monitoring what is the state of AI, I think that we can make some judgment about where AV development will go. Let's look at this diagram. The narrow AI, which I think that we already passed, I would say is very closely related to level 1 and level 2 autonomy. We do have active safety features that really comply with this definition of narrow AI machines that can perform a specific task better than a human. For instance, some of the active safety features are performing not worse than the way that people perform that. For instance, adaptive cruise control and lane keeping features can be a very good substitute for specific human behaviors. I would say that in the AV development, we are probably in this intermediate phase that is characterizing the broad AI. We are approaching the level 3 autonomy. Tesla pretends that already has level 3. This is questionable. Other OEMs also are very close to declaring success in level 3. So I think that this to big extent corresponds to this intermediate air. I would add to that also the success of Waymo, which already demonstrated autonomous driving in a confined area. But the level 4 and level 5 type of autonomy, I would say, will be achievable only when we get close to the general AI, in which a machine can perform intellectual tasks at the level at which human perform. So this is in conclusion, my prediction about the state of autonomous driving in relation to the state of AI. With that, I would like to thank you for your attention, and I'll be happy to answer your questions. Thank you.
Thanks a lot, Dimitar. Really very insightful talk, and thanks for sharing some case studies, but also your vision about the future of autonomous cars related to the usage of AI, like reinforcement learning techniques and beyond. So probably to interact with you, I have 2 questions for you, and then we'll go and answer the questions from the audience. So my first question, probably you are aware, for example, that Tesla, they are claiming to use the shadow software concept in order to actually collect more data, even when there is no need to actually collect data, like to recognize some environments in the future for better path planning and so on. But all of these concepts, like shadow software combined with reinforcement learning, deep learning techniques, they are very expensive, especially in the context of embedded devices and in the car, while we may not even have access to cloud resources, and also we need to deal with challenging real-time constraints. So what's your perception in terms of finding this trade-off between handling complex AI algorithms, sometimes like reinforcement learning? You showed how you can reduce it, the space of the learning by using even some simple rules, and actually getting the best results out of this algorithm within very constrained environment, like embedded devices in the car.
Very good question, and it's a difficult problem. Of course, many of the tasks that I talked about relate to the process of development when we are essentially training the network, and at the end, of course, we end up with a network model that is being implemented in inference mode, so the computational requirements are not so significant, but still this is a major issue. And I think that this is one of the open issues. There are so many. I talked only just with about few open issues in autonomous development, but the implementation in embedded environment, it's a huge issue. It was interesting work to observe last year some preliminary results of a study that was done by a researcher from Rice University and Intel on transforming networks, deep networks into much simpler structures that can learn in embedded environment. Also, there is also extensive work on hardware solution for transforming and for transforming the deep network structures into a simpler structure for implementation. So I believe that this is one of the problems that is being solved, and that can be solved. There are many other issues, and I would say the more complex issues are related to the fact that the theory of AI is not developed to the extent that can address all these questions, and the theory related to decision making, for instance, in uncertain environment, in a changing environment, and so on. This is really something that is a big challenge. I think that this is an inspiration for graduate students that are attending this talk.
Yeah, thanks a lot, Dimitar, for your insights. My second question, and probably my last question before we turn into the audience, it's more about the explainability part, or XII, and you talked about this in your keynote. So in many domains, like including online retailing, for instance, the vice president of eBay in his keynote in day 2, he talked about all this legal and actually formal frameworks and obligations in order actually to formalize the way how we should explain the results of AI system in order to make sure that we can trust it. And he even talked about this process that should involve even external reviewers to evaluate this explainability results. So if you talk now about the automotive domain, could you give us some insights about what could be probably existing or potentially, in the near future, the possible formalization of what we explain in order to trust an ML AI algorithm running in autonomous cars?
I think that the work on explainability has become a very hot topic in the last couple of years. I have not seen anything so far that can be considered as a solution to this problem. Probably this is why still I would say rules are one of the main tool that is being considered by the developers. By the way, nobody talks about this, what type of decision-making algorithm is being used in his system. But I strongly believe that rules are considered an important part of the solution, because they are explainable. The rules are essentially like a lookup table. You can run it and you can be sure what the output of that will be at the end. By the way, we know very well from the traditional vehicles we use very much lookup tables, just because of that lookup tables are very predictable. You know what the output of the table will be. And similarly with what is encoded in the rules. How this will develop further related to much complex structure like deep network structure is a question. I think that the approach of approximating the network with another alternative model, like a rule-based model, is one of the options. And it might be not only necessarily only with the rules. It can be a combination. It can be approximation with like a combination of neural net models. So the approximation approach is possible, probably one of the possible solutions.
Yeah, thanks a lot, Dimitar. And there is, of course, I mean, many challenges, as you mentioned, for grad students and those who really want to embark in doing research in this field, like how to deal with the complexities of these rules and also potential conflicts and how we can make a higher level of abstraction rules. So thanks for all of this insight and all of these challenging actually problems that you are raising through your keynote. Thanks a lot, Dimitar, and we'll move to the audience shortly. Thank you.
Thank you, Marwan. Thank you, the audience. It has been always a pleasure to interact with faculty and students from University of Michigan in the Dearborn campus. We have worked for a long time. We have very good relations.